Okay, so here we have a revolving door in frigid Southern California. We don't have these very much, but how many of you were in places over the break where such things are more common? Only a few. Okay, so maybe you could explain for the Californians why these make sense. Where? Sometimes. Thanks, Anya. All right. So why do they make more sense in a colder climate? So if you have a door that you prop open, then presumably a lot of warm air goes out or cold air comes in. But if you construct a revolving door appropriately, it's never really open between inside and outside. So you cut down a lot on the heat flux through the door, which, if it's cold, is a good thing to want to do. But the only way that you manage that is if you have a nice seal between the edges of the door and the round enclosure. So we're going to come up and push on the door, which is composed of 3 identical uniform panels. They're probably glass, and we're just going to treat them as uniform rectangles. We push in the middle, but there's going to be friction because of those seals that try to keep the outside out and the inside in. And so they're going to oppose the motion. And so we need to try to figure out, as we push with a force Fp at this distance d/2, how rapidly will the door begin to accelerate angularly. Say again? Aren't only, well, aren't only 2, probably, but not in this example. This is a really futile, you can never leave, okay? You're stuck in there. This is, that's right. This is the revolving door of the Hotel California. It's actually an energy generation device. So you just keep pushing and it, all right, fine. Yeah, I think Franz Kafka must have described this at some point. All right, so we have a force of the push there, and that's at distance d/2. And we have friction that opposes the motion. And since there is motion, I'm going to call it F sub k. There was a question? It went away? It went away. Question?
Oh, I was just going to say that it's easy to assume that the door is really thin, and then that makes it, then you can assume that there's friction on all of it.
He says it's easy to assume the door is really thin. Oh, yes, right. So we have an exit path that's sort of that big. Yeah, good point. All right. This is fine. Okay, so now I need to figure out, how do I apply torque equals or causes the change in the angular motion? Well, okay, I guess that means I need to figure out the torques, and then I need to figure out the moment of inertia. So let's do torques first. What are the counterclockwise torques? What's that? Yeah, so the question is, what do we want to pick as our axis of rotation? In this case, even though it's kind of a crazy example, it's not so crazy that it doesn't have an axle in the middle, and that point is fixed. So it rotates without friction around that point. So I propose that we use this point Why? Because there could be big forces applied there if we're going to be shoving it up. Unless there are reaction forces at the axle, this point might want to translate, and that's not allowed. So I don't want to have to calculate those forces, but if I pick as my axis where those forces are applied, they don't produce a torque because our perpendicular goes away. So I'm going to choose right there as my origin for computing both torques and what else? Well, moment of inertia. They both have to refer to the same. So what is the counterclockwise torque? Let's see. That's this way. That's caused only by the pushing force. So that's and the clockwise torques, well, there's 3 of them, and they're all the same, 3Fk times d. So we've dealt with the torques. I think I'm going to be more comfy if I put down a direction that I want to pick as positive for rotation. In some problems, it's going to go one way. In some problems, it might be more natural for it to go in the other direction. So this way, we're trying to shove it that way. I would recommend that we pick this direction as being positive for the angle. In fact, we might measure the position of this point of contact with respect to the horizontal as our angle theta. Okay? That tells me which way I want to treat as positive for the torque and which way negative. So the net torque, in assuming this direction as positive, treats counterclockwise favorably. So that's Fp d over 2 and minus 3Fkd, which is opposing. All right, now, how do I calculate the moment of inertia for the door system? So these things are, right, we're looking down from above. These things are rectangles. Can I just stomp on them and shove them all in and convert that door, in essence, into a rod as far as computing the moment of inertia? Will that work? Because basically, it's not changing any of the distances from the axis, and that's what matters for calculating moment of inertia. I have to sum over all the masses, the product of the mass and its distance from the axis squared. So if I stomp on it, that doesn't change any of the distances from the axis, so that seems fair. So this is just the sum of 3 rods rotating about their ends. Did I tell you what the mass of the door? Each door was m. Okay? So what's the moment of inertia of one of them? Do we remember? 1/3, mumble, mumble. Okay, so mumble, mumble. I rod about its center would be 1/12. And I rod, not a rod, about its end would be 1/3 md squared, and we could get that from the parallel axis theorem, because to get to the end, this is about the center of mass, so the parallel axis theorem says that if I'm rotating about an axis that's parallel to the one through the center of mass, but displaced by a distance little d, that I can add to the moment at the middle through the center of mass, plus, in this case, d over 2 squared. And 1/12 plus 1/4 gives you 1/3. Okay? All right? So we're almost done. We have the torque, we have the moment of inertia, and therefore let's see, torque Fp over 2d minus 3 Fkd must be equal to, what's the moment of inertia? Md squared, because I have 3, maybe I should write that, 3 times 1/3 md squared. That's I times the angular acceleration, theta double dot. Okay, so therefore, the angular acceleration, you can see one of the factors of d divides out, and we get 1/2 F push minus 3 F friction over d and m. Thank you. Okay, so let's check dimensions and make sure, because I was poised to screw everything up. So F has dimensions of mass, length per time squared. We're dividing out mass and length, so we just have per time squared. Is that good? Yep, that checks. So the angular acceleration should be given this way. And is that a constant? Yes, it's a constant, so therefore, what am I allowed to do? Well, let's see. I can certainly always integrate. But this is just a constant. In fact, I'm going to call it alpha. So this is just going to be alpha t if I measure time from when I start pushing and it's at rest. So this would be alpha t plus omega naught, but that's 0 because I start from rest. And I start pushing at time t, so I could integrate again to get the angular position as a function of time. And that's going to be 1/2 alpha t squared plus theta naught. But I chose to measure theta from 0 at time 0, and so I would just get 1/2 alpha t squared. Okay? So this is going to look a lot like your friends, the kinematics formulas, which I despise. So you should be very careful, and you always have to justify that the angular acceleration is a constant before you can use those. Otherwise, integration always works. Yes?